Hey guys, this is Simon with another Houdini tutorial, and today we want to talk about fracturing in Houdini. Because that's actually the one thing that most people try out first when they start with Houdini. Because that's of course something where Houdini is pretty strong. And there's some problems with normal fracturing in Houdini, and I learned a nice technique to increase the level of detail of your fractures, and I wanted to share this with you. So first of all, let's create a simple fracture, and then I show you what the problem is. So I create a geo and maybe a torus like that, and then I will create some points in the volume of this torus, simply with an ISO offset and a scatter. We will do this again in a second with our own setup, so you don't have to pay too much attention to this. Voronoi fracture. Alright, so let's connect this here and visualize the pieces. So the fracturing in Houdini is pretty simple, but the problem, as you can see, is that our cuts are always totally straight. So we have those nice voronoi chunks. Even if I increase the amount of fractures, we have nice shapes, but the cuts are always perfectly straight, and also the inner side of those fractures is also like a perfectly straight edge, or we don't have a lot of detail on the inner faces. And there's a nice technique how you can avoid this, or how you can increase the amount of detail of your fracture. So let me go back and delete this one. So we'll start off with an empty scene. And before we start, I want to show you in theory how this technique works. So I have this piece of paper here. Imagine this is our model, maybe a simple grid. And if you would simply fracture this, something like this happens. So you get a perfectly straight cut out of your fracture tool. So this technique is called pre-fracture transform, which means before we fracture the object, we crumple it like this, so we distort it like that. Then we make our straight cut like that. And then we morph it back, so we invert the distortion. And if we morph it back, then you can see that we don't get a straight cut, we have a nice edgy cut here, which is very irregular. So this is basically what we're trying to do today. So let's create a geo node and call this one pre-fracture transform. Dive inside, delete the file node, and maybe we simply use the rubber toy, the test geometry which comes with Houdini. And maybe let's delete all the colors and stuff with an attribute delete. That, and simply type in star in every field. Oh, not plus. Star, 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 star. Then you should have a clean model without any textures or attributes on the points. Alright, so first thing which I always like to do is place a null object here, just in case if you want to switch the input geometry, then it's a little bit easier. If you have a port here, connect that, and we call it in geo, so that we know this is our input. And I usually like to color code this, so make this a light blue. So this is where everything starts. So let's create a voronoi fracture. So this is the node which will actually break up the geometry, and this has a few inputs. So the first one is geometry to fracture. So in here we connect our geometry. And the second port, which is important for us, is points for voronoi cells. So for the voronoi fracture, you need to give the voronoi fracture tool some points that it knows where the fracture pieces should be. So the easiest way would be simply to scatter points into the volume of this object. So to do so, we first have to convert this model to a standard Houdini volume. This is pretty easy with the ISO offset node. Connect that one. Put the flag here, and then you see a rough shape of our object, and maybe increase the subdivisions to something like 50, the uniform sampling divisions. then we can see the rough shape of our object. And if you now create a scatter node, which usually places points on the surface of our object, if you connect that to the ISO offset, it will create points inside of the volume. And we can maybe decrease this to 50 for now. And these points are now connected to the second port. Put the flag on here. And if we click on the voronoi fracture and say visualize pieces, we should see that our model is nicely fractured here. Okay, so now we need to build this pre-fracture transform thing. And to do so, we should first of all store the initial position of our points. So basically, every point here should remember its original position so that we can morph it back afterwards. So there are several ways of doing this in Houdini. For me, the simplest way is to use an attribute wrangle here. If you are in Houdini for some time, you start using wrangles and write like tiny bits of code. You don't have to be a coder for that, but it's just, in my feeling, it's less work to use a wrangle in this case. So we'll take an attribute wrangle and plug it in between here. And we call this one store initial position. And if we click on the wrangle node, we have a window here to write in some code. And I will open up the geometry spreadsheet here that we see what kind of attributes we have stored in our model. So at the moment, our points, those are the point numbers, only know their position. There's no more attribute stored on this one. And we can simply create new attributes here. So position is a vector. So basically we want to copy those attributes into a new attribute which simply has the same values but another name. And this should also be a vector. So I start my code with v for vector, at init pos, this is initial position. You can call this whatever you want. And that equals at p. So capital P is the variable for the point position, and end your line with a semicolon. And when you click somewhere else, you see that we created a new attribute which is stored on each point, and this new attribute is exactly the same values as our point attributes. So the good thing is if we now change our attributes here, the point positions, it will still remember the original point position here. So let's transform the whole thing. Maybe with an attribute vop. And we plug that in here. No, sorry, not here. Here. So we store the position first, and then we distort our model. So this is called pre-fracture transform. Put the flag on this one, dive inside. Maybe a little bit more space here. And let's create a turbulent noise. Connect the point position to the noise, because each point has to sample its own position to look up what the noise value in that position is. And we need to make sure that our turbulent noise is set to a 3D noise. And then we create an add node and add the current point position. So the position where the point is right now, we add onto this one the vector that comes out of the noise. And the result will be the new point position. So then it looks something like this, totally weird and destroyed. But that's fine. And then we want to expose some of the parameters of our noise so that we can adjust it outside of this network. So to do so, just middle click on the port, maybe type, middle click, promote parameter, then you get this knobs, which means it's accessible from outside now. Maybe also the frequency, the amplitude, I think that's fine. And if we now go outside, one level back, you see that we have all those parameters here and can change them here. So I will adjust the amplitude to something like that maybe, and increase the frequency much more, that it's more like that. And maybe let's not take an alligator noise, but maybe zero-centered Berlin noise. And we just get this wobbly surface here, maybe a bit more. Something like that. So frequency of 3, zero-centered Berlin noise, and 0.5 amplitude. So now it's nicely crumpled. And if we now take a look at our fracture voronoi, it will look like this. So our cuts are still totally straight because it's simply the voronoi fracture, but our model is distorted. And now we can morph it back to the initial point positions, and after that our cuts will be distorted. So there's again several ways of doing this. The super easy way is simply copy this point attribute wrangle node that we created earlier. And this one is called restore initial position. And we simply have to turn this one around. So now init position doesn't equal position. Now our point position should equal the init position. Semicolon at the end, at p equals init position, like this. If we connect that now and morph it back, we can see that this worked. The normals are wrong now, but we can fix that pretty easy. But if we take a look at our cuts, they're now nice and not straight anymore. And we have a lot of detail on the surface. Alright, so this is step 1. Let me just create a normal node to align the normals again. This, then we have the nice surface. And it looks pretty good. You can't distort it too much because then you get some artifacts, something like that here. That was too much. So we have to adjust that maybe in our pre-fracture transform, maybe 0.4, and then it's gone. So you have to play around with those values and check when it works well. But this is definitely a nice technique to increase the amount of detail. Alright, if I now connect an exploded view to the end of this one, we can see that our outside faces now look perfectly fine, but the inside faces actually are still totally straight, and we have a lot of artifacts here because it's now n-gon sides here which are distorted on too many points. So we want to create more polygons on the inside and then also distort them in a similar way. Okay, so if we take a look at our voronoi fracture node, you can see that it creates groups for us, inside and outside group. You can also click on this button here, this one, then you can see the groups, and we can see, which are highlighted now, we have an inside group and an outside group. And this is super handy because actually we want to remesh the inside group. So let's try this. I'll just build that here in between, maybe like that. We'll just put the normal node at the end of our chain. So remesh, connect that one here. And we only want to remesh the inside group. So group, inside. And now with target edge length we can adjust how dense the mesh should be. I'll set this to 0.05. And then we get nice detail in here. And we still have the jagged outsides, so this is totally fine. So now the inside is meshed. Alright, so what we want to do now, let me just decrease the amount of chunks here so it's easier to see. Maybe 10. Okay, what we want to do now is create another attribute VOP where we use the same technique as we used here. So we will create a noise and simply add the value of the noise to the point position of the points. So let's do this. Attribute VOP. And we call this distort inside. And maybe put the flag on the exploded view again that we can see it. And let's dive inside here. And we do the exact same thing. We create turbulent noise, connect the position of the points to the noise to sample the noise, set it to 3D noise. We can change all this stuff later. Create an add node and add the current point position to the value, to the vector of our turbulent noise, and connect that to this one here. Alright, and I will promote the type and the frequency, and we will take a look at the amplitude later. So maybe I'll just, for the sake of seeing it, I will just change the amplitude here to a small value, and then we go back one level and increase the frequency. Let's see, something like that would be cool. It's still a bit too strong, so maybe amplitude 0.1. Nice. Okay, now you can see that we created some more surface detail using this noise. The problem, of course, is that it will not only distort our inner pieces, but also the outside surface, and we don't want to do that because we wanted to keep that shape. So what we want to do is, if we take a look at this one here again, and maybe disable the visualize pieces, we basically want to weight our deformer that we built here so that it has a lot of weight on the inside pieces, and when we get closer to the surface it should simply like blend out so that it has no effect on the surface but full effect on the inside, and in between here we need a smooth transition so that it starts to deform in here. Alright, so how do we do that? We push that here down, the distort, and after our remesh node we want to split the inside and the outside faces into two groups, or two streams of our node graph here. So we create a blast node, put it in between, and in the blast node I'll type in inside and say delete non-selected, so I can call this one inside. So now we only have the inside pieces here. This is again the group that the Voronoi fracture gave us, and we copy this one and call it outside. And here we also want to keep the group outside, make sure that delete non-selected is checked. So this is now only the outside pieces. If we go to wireframe mode we see that it's hollow. And this one here is only the inside pieces. And now we can give them weights. So basically that means in Houdini that we also give them an attribute here with that the points know how much they should deform. So to do that we can use an attribute create. This is of course also possible with an attribute VOP, but if you just create one attribute with a plain float value, I think this is easier. So deform weight, and we call this attribute up here deform. The class is point because we want to save it on the point, and on the inside we want to have a weight of 1. And we can see here, now we have this attribute called deform. All our inside points now know that they should be deformed by 100%. Now we copy this node and put it on the other side, and the deformation weight for our outside points will be 0. Alright. And now we have to blend them together so that those points here who have a weight of 0 and this one who have a weight of 1, that the transition between those two is smooth. Right, and for that we can use an attribute transfer. The attribute transfer node is pretty handy because it can transfer attributes from one point to another based on proximity. So if one point comes close enough to the other, it will inherit the attribute that you specify here. And under conditions you can say how big this distance threshold is, and what's even more important, you can also blend, so you can blur the border between those two values, but you will see that in a second. This one has two inputs. The first one is geometry to transfer attributes to, and the second one is geometry to transfer attributes from. So this is our source and this is where we want to transform it. And basically we want to transform the attribute of our outside points onto the inside points. Connect that here. So we call that blend weights. And to visualize that, we can hover with our mouse over the output port here and press X, and this will create a visualize node. That is pretty handy. I think it got introduced with Houdini 15, if I remember correctly. And at the moment, if you click on it and go to visualizers, it simply visualizes the position in space as a color. But we want to see the deform attribute, so type that in here. And instead of attribute as is, we set that to ramped attribute. So we see that ramp here, and the range min-max from 0 to 1. So blue means a weight of 0, and red means a weight of 1. And let's take a look at our attribute transfer node. So first of all, we have to make sure that we transfer the right attribute. So it's a point attribute, and it's called deform. And under conditions, we can see that the distance threshold is super big. So at the moment, everything has a weight of 0. So if we start to shrink this down, when you are at a very low value, you can see that it starts to fade in. So maybe 0.1 is a good value. So right now that would mean all of those points here don't get deformed at all, and those are deformed by 100%. So this is a pretty sharp border here. So we can use the blend width and simply blur that out and maybe decrease the value even more, something like that. And then you have a nice and smooth transition of the weight of our deformer. And you can also check another kernel function, maybe the blend model, which gives another fall off. But that looks pretty good to me. So we now have stored our deform value on our points. So if I scroll down here, you will see there are also some points in between, which are the transition areas here. And we now want to use this deform attribute to control the strength of our noise, which is here in our distort inside node. So let me activate that again. And of course, what I forgot is, out of this attribute transfer node is only coming the geometry which is connected to the first port, which means we only have the inside pieces at the moment, but we want to have the inside and the outside, of course. So we have to merge them back together. So create a merge, plug that in between, and take our outside group also, after you created the weight attribute, of course. Something like that. So let's put the visualizer over there. Or maybe connect the visualizer to the distort node, so we can see what we are doing. Maybe connect it to the exploded view, so we can see them pushed apart from each other. So now we can see that we have our geometry and our deformation weights, and the only thing we have to do now is tell our distortion setup here that it should use this weight attribute to control the strength of the noise. So let's dive into the distort. Let me make a little bit more space here. And here's our amplitude value, which I want to control. So now we have to bring in the deform attribute of our points. And to bring in attributes, you use a bind node. And you type in which attribute you want to import. So in this case, it's deform. It's a float, that's right. And if I would now simply connect this one to my amplitude, the value would be pretty high. You remember that I set the amplitude of my noise here to 0.1 because everything else is too strong. So if I connect that now, it will look pretty crazy, but you can already see that the outside faces are not affected at all. Just the inside faces are totally destroyed now, which is simply because the noise is too strong. So we have to map these values, which range from 0 to 1, to a new range. For that, use a fit, and in the fit we simply expose the destination min and the destination max parameters. Double click on the knot to unfold those nodes here, and then we give it new names. So the label should be minimum noise or minimum amp, and this one is called max amp. And if we now go back one level, we can see the control here. So here we have our minimum distortion value now. So let's set it to something very tiny, something like that maybe. And let me also check the 0 center purlin maybe. Increase the frequency a bit, that we get more detail, something like that. And in theory, you could use the min amp value if you also want a little bit of distortion here on the surface. So if you do something like that, then also the outside gets distorted, but that's just to have more control. But basically, that's the whole setup. So you now have pretty good control what is distorted and what is not. And if we simply go back up here and take a look at where's our remesh? Here's the remesh. And decrease the value here to something like 0.02 maybe. And we should get much more inner detail here. That looks very nice. We can see that the noise is maybe a little bit too strong. So let's adjust this. Max amp 0.1. Yeah, nice. That looks good. So now you have a full working setup, and you can simply switch the input geometry over here. So let's try something else. Let's simply try torus and put that in. So then the calculation runs again, and you have a fractured torus with nice distorted inner walls. And you can always go in and change those parameters here. Maybe the frequency, make it a little bit bigger, increase the maximum amplitude. And since all this distortion happens while it's not in this exploded view, but they are like perfectly connected, the pieces should stick very nicely together. So this shape should exactly fit into this shape. And here in this example you can see also that we have some problems here because the inner pieces are pushed too much outside. So we should simply increase the fall off here of our weight. And we can do this here in our blend weights. So simply increase the distance threshold to 0.2. Maybe this one further, even more, 0.4 maybe, 0.05. So you can play around with those values until it looks however you want. Yeah, and this is basically the setup. So it's a nice technique to adjust your fractures that they don't look like perfectly aligned voronoi fractures. You get detail on the cutting edges and detail on the inner faces. So I think that was actually one of my fastest Houdini tutorials. Nevertheless, I hope you liked it, and let me know what you think or what you want to see next. And oh, by the way, big shout out. A lot of people write me emails after my tutorials, how I started to learn Houdini and if I have good resources for them. Make sure to check antagma.com. Nice new training website made by my friends Manuel and Moritz from iXponsa. They produce very, very nice Houdini tutorials if you want to get into Houdini and also advanced Cinema 4D tutorials. So make sure to check that out. Even if you're not interested at all in 3D, you should listen to Moritz's voice because it sounds damn sexy in these tutorials. Alright, so see you next time with the next video. Bye bye!